This webinar is about workflow based on OpenFOAM, so it's presented by in a partnership by both Creative Field, that is editing software such as cfMesh and CfSuite, and Genias Graphics, who is a distributor of Tecplot within Europe. My name is Antoine Leijer from Genias Graphics, and I'm presenting today with Tomislav Lugaric from Creative Fields. So today's summary, a brief introduction about Creative Fields and Genias Graphics, and then we will present some example of workflow from data that is issued from tutorial from OpenFOAM. So first case study will be heat transfer in a Flange. Meshing and solving will be made with cfMesh and LaplacianFOAM, and visualization with Tecplot 360EX. Second case study is a CFD study on a S-band pipe with CfSuite, cfMesh, solving with icoFOAM, and post-processing within Tecplot 360EX. So we'll end up with some conclusion, and then we will be online for a few minutes so we can have a discussion and answer any question you may have. So Genias Graphics, we are the exclusive distributor of Tecplot within Europe. We are providing solutions for visualizing and analyzing scientific data. There is approximately 1,300 organizations using Tecplot within Europe, and we have more than 20 years of experience in doing so. We are based in Regensburg in Germany, and we are doing some training, some consulting, as well as some software development. Our largest customers are mainly issues from aerospace domain, such as Airbus, Dassault Aviation, or JLR, and so on. So Tomislav, I will give you the presentation for following.
Of course. Hello, I'm Tomislav Lugaric from Creative Fields. So first, I will give a short introduction of our company. So we are a startup company founded last year in February, and we are based in Croatia, in Zagreb. Our two primary products that we will show today are cfMesh, which is an open source library for automatic mesh generation, which is built on top of OpenFOAM. And the second product is CfSuite, which is our commercial product, which is a cross-platform graphical user interface for meshing and pre-processing for OpenFOAM. Our key goal is to provide tailor-made solutions built around the OpenFOAM framework, and to that extent we have developed CfSuite not as a fixed GUI but as a framework that can be adapted to all the customer's needs. So I will now show you a basic workflow with CfSuite. So we will start our first demonstration with the Flange case. So I have already started my software, and I will now first create a new project. We will place it on the desktop. Sorry. I will create a new project. We will locate it on the desktop so we can start working. I have already. Okay, so now we have an empty project, and before we can start any pre-processing, we need to create a new case. Let's call it Flange, for obvious reasons. Now that I have created my new case, here I have an empty project and an empty case called Flange. The first thing I want to do is to import a geometry. I already have a geometry prepared in the STL format, but for needs of our application we use an FMS format, which is basically a triangulation, a typical font triangulation with some metadata added. So in order to convert any file type such as VTK, STL, or FTR into our format, we can use the built-in tool in our application. We simply go to the ribbon, click Convert to FMS, select the file that we want to convert, and just run the process in the background. Now the process will take a short time to run, and when it's finished we can import the geometry. We simply go to our project tree, import the geometry, go to our file, and now we have the geometry present in the project tree. Now on this geometry we already have a few predefined patches, but they are all of type empty patch. For the purposes of the simulation, we'll convert those patch types into patches. Now we can start to set up our meshing case. Typically in the ribbon, the workflow is to simply go from left to right. From left to right. And so first we will adjust the meshing settings. As we can see from data about the flange in our information window, the flange is dimensions are roughly around 0.05. So we will use a cell size of, we will use this cell size for the main cell size. We also have this tool that allows you to preview the cell size in relation to the object. So this way you can drag the little cube around all features and confirm that the size is okay. We will also use this boundary cell size setting to have finer cells on the boundary. Now we have set up our mesher. Typically, if you already have mesh dict in your case, you will get this warning. It is usually safe to ignore it because it just means that we need to refresh the dictionary. But for example, if you've already done meshing before, it just warns you that you might lose data if you continue. So now we have adjusted the mesh size. One more thing that we need to do for our mesher is to set which feature edges need to be captured by the mesher. Our mesher tolerates, for example, when you have non-perfect mesh, which is not joined at the seams. But for this reason, it is advisable to specify the feature edges. So now I will use the automatic generation tool to generate the edges. And as you can see, most of them have been captured, but a few of them are lacking. For example, this one, and these two. I will now use the trajectory selection tool for edges. And when you click on it, it will simply add the edges to the selection. So this one, we add this one, and this one. We can reduce the transparency just to make a short check, and all the edges are here, so I can now add them to feature edges. Now you can see that there is a tick mark here, meaning that all the feature edges have been generated. And now basically this is all we need to begin the meshing process. You can use these advanced settings if necessary, and we will use them in the next demonstration. But for now you can simply choose which mesher you want. The tetrahedral, we can use the tetrahedral or the Cartesian. For this simulation, Cartesian will produce a better mesh, so I'll use that one. And this Cartesian 2D is usable only for specific solvers. So now we start the mesher. It starts as a standalone process, so now here you can see the console output of cfMesh running in the background. Now the process has ended, and we can now see the mesh is available in our project tree. Now here you can see that all the feature edges have been captured. In addition to the edges that we specified, you can also see that this edge was captured. And this is because in addition to edges that you have specified yourself, Mesher will also capture all the edges that are located on the border between two patches. So now that we have completed the meshing, we can also do some more inspection of the mesh. For example, we can clip it using the clipping plane tool, and now you can see on the inside of the mesh. So here you see the effect of the boundary layer cell size. So here we have finer cells, and on the inside we have a cursor. So now we are ready to start setting up the simulation. So initially you'll see that in the ribbon we have only the Measure tab and no solver is selected. Now we can select the LaplacianFOAM solver that we will use, and the ribbon has reconfigured itself, and now we have the solver tab. So now we can start setting up the simulation. Again, the workflow takes us from left to the right. First, we will set the thermal diffusivity. And here you can see I can either enter it directly, or I can use this button to load it from a set of predefined. So here basically we have a mini database that we have built in, but this database, not only that we have one built in, but by writing XML files with properties yourself and placing them at the appropriate location, you can expand this database. Next step, we will set up the simulation to simulate for 2 seconds with a time step of 0.1. Our application will set up the defaults for the solver, and for this simulation we can use the defaults, so we don't need to click on any of these buttons, but if we wish we can just click and check if the settings are what we wish them to be. Next, let's set up the initial conditions. So for the initial conditions, we will use 273 degrees Kelvin, and we will set up the boundary conditions. So for the boundary conditions, here you have the list of patches, and you can enter settings for them. You can either select patches from here, but if you wish to see for which part of the geometry it's used, you can either click directly on the geometry, or you can click through the project tree. So we will set patches 1 and 3 to 0 gradient. We will set patch number 2 to 273 degrees. And we will set patch 4 to 573 degrees. And so now we have saved all the settings, and we are ready to begin the simulation. So simply, next button in line is Start. You can start the simulation, and you can see again console output from the solver, and in addition there is this plotter which shows you the residuals. We will show this plotter in more detail in the next simulation, but for now you can see how we are basically parsing this output, capturing the numbers and plotting them here for you. So now we can see the simulation is done. There is a tick mark here. The application reports the results are present. So the next button in line is the Tecplot button, because our application is one example of such. And now by clicking on this button, I can invoke Tecplot, and automatically the data from our simulation will be loaded into Tecplot. So for further demonstration, I'm handing over the presentation to Antoine. Thank you for your attention.
Thank you, Tomislav. So regarding the post-processing, it will be done within 360EX. We've got a direct interface to CfSuite, as you just saw. We also have an improved OpenFOAM data loader. Our new interface allows actions such as context-sensitive menus, accessible on right clicks, for example. And I will show you all the classics of visualization, such as contour slices, trim traces, and so on. And they're all right at your fingertip, as you will see. So for the flange, we will basically realize kind of a little visualization like this one. So here we have quite rich animation with contours, vectors, trim traces, and so on. All right. So I will start Tecplot 360EX. I will start from scratch and opening a file. So that's the Flange file. This is a typical OpenFOAM data. You've got one repertory per time step, and then you have 3 repertories with constant meshes and system. And within that system directory, you will find that control-dict file that basically gives you information on where is what data and how to load it. So Tecplot is currently loading the file. So what we want to do within that flange first is, well, I will withdraw that bounding box here. So what we are interested within that flange is basically to see what's happening inside the flange. So we will use that value blanking tool that basically allows you to not display some cells regarding a constraint. So for example, here I will get it in the plane of symmetry within X. Now regarding the data itself, so you can access all of the information you need about your data within that dataset information plane. So basically here we have three variables that are X, Y, and Z, and those are corresponding to the geometry itself. Then we've got the temperature and the gradient of temperature. And then we've got other data that we are not going to use right now. What we would like to do is basically to calculate the heat flux. And to do so, you can specify equations. So heat flux, for example, equals minus K, which is the thermal conductivity, by gradient of temperature. So that's basically the equation we wish to perform here. Within Tecplot, you can save and load equations. So I already saved those equations here. So just by double-clicking them, I can load them within my equation dialog. Here I choose 24K, it's approximately steel. And so I'm calculating each component of the vector. So by clicking compute, Tecplot is computing each component one after each other. So as you can see, it's written here in the bottom. And that's it. So now I've got a new, well, three new variables that are my heat flux variables. So within Tecplot, you can have all of your visualization classics right a click away. So for example, if you wish to display the mesh on all of your zones, you can do it just by toggling on that little mesh button here. But you can also, on a zone, decide not to display a mesh just by right-clicking it. All right. Now I will speak about contours. So here is a transient case, means on the solution time slider here, we have basically the convergence of the code and its output during the simulations. So I will go on the last one, and I will first change the coloring of my temperature. So I will take diverging blue to red. So basically blue is cold and red is warm. And I will enter new levels for my contour. So for example, you can define levels from 250 to 550, and having a delta of 50 makes you 7 contour levels. And here is your result. You can have either banded or continuous coloring, and that's it for the contours. Now a second grand classic of visualization is to explore the volume itself. So you can toggle on slices, and while pressing, for example, another axis such as Y, you can put that slice on a Y axis. Now I will speak stream traces. So once again, slice is an object, so you can decide, for example, to have it shaded instead of having a contour on it. That's up to you, but you can basically access all the thing you wish to visualize one right-click away, such as the mesh, the contour, vectors, shading, edges, or translucency, for example. All right, so now we will. I will just put contour on my mesh so we can see it. Now we will speak about stream traces. So you can basically define stream traces. You have within your plot that vector data that you can basically specify which variable you wish to use for your vector, and we will here take the heat flux. So Q, X, Y, and Z. And now we can seed stream traces either one by one or as a rake. So I will seed a couple of. You can also seed those stream traces randomly on your surface of a selected object. So here would be the slice, for example. And here it is. I've got a couple of stream traces here. And I will just turn it a bit for you to visualize. So that's basically the stream traces along which the heat flux goes. What you can do is that you can color, for example, your stream traces by a given contour. So here would be the temperature, and that's it. You can also display vectors. So for example, here would be the vectors and the flange itself. You can also make them a bit longer, for example. So we'll do it interactively here. All right, and that's it. Well, here we don't really see those stream traces. So what you wish maybe to do is just change the background of your frame. So you've got a black background. Of course, you need to change the legend coloring as well as the axis coloring, so you can see it better as well. And you can drag and drop everything to make it easier to within your display. So now a little tool that I wish to introduce to you is how to animate and export animation, for example. And there is that keyframe animation tool that basically allows you to append some views one after each other, and Tecplot would link all of those views together. So let's say you zoom in, you rotate, you zoom out, and that's it. So you can use that tool as well to go back from one view to the other just by selecting the view and clicking apply. That's a nice way to store your views within Tecplot. If you've got some, I don't know, if you're interested in a detail here, you can just have that view stored and come back to it quite easily. So you can animate everything, and basically Tecplot is linking all of your frames together, and so you have a nice animation. You can either have it on screen or export it to a file, and so on. So I guess I will stop it because I guess you got the idea behind it. All right. So one last thing is in order to save time within Tecplot, you can load and save frame style. So I already saved one, and I will load it. And basically, it gives you the exact layout you had at the time. So thank you very much. That's it for the basics of visualization, and I will get off back to Tomislav. Tomislav? I'm sorry, Tomislav, we cannot hear you.
Can you hear me now?
Very, can you make it louder?
Just a moment. I'll try. I'll see if I can boost my microphone maybe. Oh.
Yeah.
Is it fine now?
Yeah, it's very good. Thanks.
Okay. Sorry for the inconvenience. Okay, so we are back in our project. We have this Flange case, and now I'm going to import a case that is already partially prepared. So I have prepared this S-band case. Now we have to give the application a few seconds to load it, and now we have a case with the geometry that's already prepared. Now, as you can see in the project tree, this geometry already has feature edges generated, but we only have one patch. So now I'm going to show our selector tools that can be used to generate patches. So we have a few basic tools like clicking on individual, doing rectangles, and we have this critical angle that I'm going to use right now. So what do? I set the critical angle, and when I click on the geometry, it will select all the facets until an angle greater than critical is reached. So now I'm going to generate patches. I'm going to use this patch as a symmetry plane. I'm going to use this patch as inlet, and I'm going to use this patch here as the outlet. The rest of the geometry that you can see here is will be used as a wall Currently it is named object by default. I will simply rename it to wall. I will also set the patch types, so these two are correct, and symmetry plane will just set that it's of type symmetry. Again, I will do the meshing setup. So we will use a cell size of 0.1 for the maximum cell size, and now we will do some local refinements. So we will do a refinement on the walls, and we wish to do a special refinement here. So for this purpose, I'm going to create a facet subset. Again, with the critical angle selection tool, I'm selecting the inside of the tube, and I will add it into this subset. Now, what's the main difference between patches and subsets is that subsets are not transferred to the volume mesh. So now I can use this local refinement to set one refinement of, for example, 0.05 on the walls, and so on the walls 0.05, and I will also add a greater refinement of 0.25, which will be active only on this subset. So now we are again ready to start the mesher. We'll use the Cartesian mesher again. And now our mesh is generated. So now when we load the mesh, we see that we have a coarser refinement here. We have a very fine refinement here on our facet subset. And when we check here, we see that the patches are transferred to the volume mesh, but no facet subsets. So now again, we are ready to prepare for our simulation. We will select the icoFOAM solver, and now we have the solver ribbon ready. We will set the kinematic viscosity of 0.1. I understand that this kinematic viscosity doesn't model a realistic fluid, but we want to show the workflow and we want to have a nice laminar flow. So for the control, we are going to set again 2 seconds, and we will have 200 timestamps. As for discretization schemes, we can use defaults for most settings. We will just change the velocity from Gauss linear to Gauss gamma. One more feature I would like to show is that our editors have a built-in help system. So each editor has a short explanation that gives you the overview of the options that you can set. So basically you have a mini manual built into the application itself. I will also adjust the gradient scheme for pressure from Gauss to least squares. Now we can start setting up the initial and boundary conditions. For initial conditions, we can use all zeros, and for boundary conditions, we will set a velocity of 5 on the inlet. And as you can see from this triad down here, that is the correct direction. For the outlet, 0 gradient of velocity, pressure of 0, fixed value 0. The symmetry plane has special settings for symmetry, and the walls, we just need to set the pressure to 0 gradient. You may also notice that there is a warning that multiple timestamps exist. And that is because we have results left over from a previous simulation. So we can use this command to remove the results so we don't get any contamination in our simulation. Now we are ready to start the simulation. And again, you can see the output from the console and you can see the residuals. Now, since this simulation will run a bit longer, let me show you a few features of our plotter. So our plotter now captures 4 residuals, and what you can do, you can turn on and off specific lines, you can limit the number of points visible, and if you want to see numbers in greater details, you can always turn on these labels. Also, once this simulation finishes, you will have the option of saving this graph as a PNG format, and you can save it as a comma-separated value, which can be useful if you wish to import it into a spreadsheet program and reprocess it yourself later. This window shows you the textual output, which can also be saved to a text file if you want to reprocess it or just to have it as a log for later. And also in the unlikely event of something going wrong, you always have the buttons for terminating and killing the process, so you don't need to go into Task Manager, or if you're on Linux, you don't need to go to the terminal. Now let's just wait a few moments for the simulation to finish, and then I will shortly show you how to export these residuals, and then you can see some post-processing. Also, if you wish to see some more advanced options of meshing or remeshing, we can do it in the question and answer section on the end. Okay, so the simulation will be over in a moment. So now when it finishes, you will see that this play symbol turns into a tick mark. So now what we can do, we can click here. So we can save a log. And here, for example, we will export a CSV file with residuals. And after this is done, you can see on the desktop we have these 2 files, and we can reprocess them. Again, now we can start post-processing by clicking the Tecplot button, and I'm transferring the presentation to Antoine again.
Thank you, Tomislav. All right. So regarding the post-processing of the SVN pipe, I will show you some advanced post-processing such as integration, fast Fourier transform, variable calculation automatically, and so on. We will also see that Tecplot 360EX gathers all kinds of plots from very simple XY line up to very complex 3D plots. We'll see that you can have many frames and many pages, and we'll kind of open a bit the presentation on the automation of Tecplot using macros or Python scripts. Okay, so I will just launch Tecplot. So I had a question just before. I will just answer it quickly regarding the different, well, whether Tecplot can work on other CFD simulations. Yes, we have a huge number of loaders. Those are the one by default, but we also have other ones that are available. So basically, I will go back to my OpenFOAM data loader and specify my control dict from that SVN case. So now Tecplot is loading the data itself. So first of all, I will just present the CFD analyzer module. So in that module, you can define, for example, some fluid properties, such as an incompressible fluid in our case here. You can define some reference values, and you can specify to Tecplot field variables. So here, Tecplot automatically recognizes that the velocity would be u, v, and w. So we'll let it like this, and I will use other state variables, such as pressure, and if you don't have another one and you don't aim to use it, you can put more or less whatever you want. I will just calculate the velocity magnitude. Means I don't really need pressure or temperature for that. So within Tecplot, you can access a automatic variable calculation. So as you can see, there is quite a number of variables that are already within the Tecplot. And I will toggle off that calculate and demand. This is to aim for people who have really big data. Tecplot would calculate that variable only on the element that you are currently looking at. However, here the dataset is not that big, so I will calculate the velocity magnitude for each point and every time step. All right, so calculation is complete, and it gives me minimum and maximum and their position, and that's it. So I will flip it over. So once again, you can, with your right click, decide to display or not to display. So here is the axis, but you can decide to hide or not display, for example, shading on some zones. So here I just kept the symmetry plane, and I will put a contour on it. Once again, within your contour, so you can define the coloring, for example. So I will take pressure in yellow or green, and let's say velocity magnitude that I just computed, and I will put it in a blue sequential contour. So you can just click here contour and decide which variable you wish to have for your contour. So here is once again a transient case where the time steps is used to show what is the evolution of the calculation and its convergence. I will just minimize those legends here, as we are not much interested in the values themselves. It's just an indication. All right, I will just display a slice. So here is actually a good place, maybe a bit further on. And well, let's color it with the same value. What you can do within Tecplot is that basically you can extract some zones from your data. So here I have a 3D data, and I wish to extract a slice over time. So basically Tecplot is extracting, as you can see, it's looping through the time steps, and it's extracting a new zone for each time step. So with that new zone, I can simply copy and paste my frame here. So as you can see, you've got a frame sidebar that basically summarizes your frames. And here, as you can see, I've got 2 frames. And this is very powerful because you can look at two aspects of your data simultaneously on the same page. I will not show the borders, and I will turn that that frame here into a 2D frame, on which I wish to display my slice, which is here, and only my slice actually. All right. I need to assign new x and y, which will be actually y and z axis. So I've got my slice here that I will color by the velocity magnitude. All right. Here I could, for example, color it, well, display some vectors on it that I could color, for example, by pressure. And I will just once again resize my my legend. And here I have a 2D plot within a 3D pages. What I can do out of it is, for example, I can use once again that analyze menu to perform, for example, an integration through that slice. What I will do here, for example, is integrate the mass flow rate. So basically what I need is the velocity vector and the density. And I will integrate it over time, and I will select as a zone my slice here that has been extracted. I can show the result either as a tabulation or to plot them. I will decide to plot them as well. All right, so here is my integration result, and I can make it a text, and that text is available here within my frame. So I will just kill it. And here I have my integration result directly within a little frame. This is a XY plot, this is a 2D plot, and this is a 3D plot. One thing I forgot to do is that you can link your frames in solution time, and I will apply it here. So all of my frames are linked together. All right. So now if I loop through my time steps, as you can see there is a time slider here that basically gives me an indication on what time step I am currently looking at, and it's updated in all of my frames. So what you can do as well is, for example, to extract a XY line plot, you can use that tool that is called probe to create time series plot, and you can probe anywhere, let's say, on the slice here, and you've got the pressure versus solution time. Once again, you probed it, but you probed not only the pressure, so if you wish to have the velocity magnitude as well, you can do that, of course. And once again, you will have a little time slider that will basically tell you at which time step you are currently looking at. All right, back to the 3D frame. A few advanced visualization tools. For the slides, for example, you can display many slides at once. So let's say between here and here, you wish to have let's say 5 slides, so 3 intermediate start and end slides. That's an option. Same for the stream traces. You can decide to, oops, sorry, I will just delete them all. You can decide to have either, once again, rake of stream traces. What you can do with your stream traces, and it looks actually quite nice, is to show some markers that you would color, for example, by pressure. And I will just put a bit less markers so we can see it a bit better. Sorry, let's save. Okay, and now you can animate your stream traces. So you basically see how the tracers are going along the stream traces. The distance between 2 markers is proportional to the velocity magnitude here. All right. I will once again resize that, having it smaller there. All right. Tecplot works with many frames, but you can also work with many pages. And here what I will do, I will add a pages. So in each pages you can have any number of frame and any number of data set, as much as you want. So here on another frame I will basically load another data file. I will use my Excel data loader, which is here. And basically that file is the residuals export from the calculation. So I will just find it here. Here is my residual. So Tecplot automatically recognizes that we have 5 variables, so the time step, the 3 velocity component, and the pressure. And this is directly the export from CfSuite. And here I've got my UX residuals against time. I will first decide to show all of my residuals, and then I can change actually whatever data I want to visualize in any possible way. Basically, it's possible within Tecplot. So, for example, if you wish to have small symbols, you have to display those. Let's say field. You can just in few clicks have those done. Same here. What we would like to do, for example, is having that plot here on a log scale, which is easier to visualize, and that's it. One last thing we could have is, for example, a line legend, so you see exactly what is what. All right. So I will now delete that that page here to show you that you can automate basically any operation you do. So you can play some little macros and scripts that, for example, would automate residual loading of a simulation. So basically that macro takes the SBN case directories that I'm visualizing here and loads the residual CSV that is within that that same directory. So in one click it creates a page and display you the residuals in the exact way you want. So that's an example on how to automate Tecplot. You can do a lot of things, and the good thing is that you can record your macros. So basically you do what you want to do and then you just play the macro and it redoes it quite easily, and you really have very few things to script. All right. So that's it for advanced visualization. We can end up on conclusions. So Well, Tomislav, feel free to comment on conclusions as well. Basically,
Yes,
sure, go ahead.
Okay, so if I may say, so basically our CfSuite and cfMesh products are mostly based on OpenFOAM, but CfSuite is designed to be a flexible GUI framework. So what we tried is to build a simple workflow that everybody can use, and although we may not have shown you many solvers right now, we can integrate new solvers, we can integrate new tools. So if at any time our customer requires additional tools or additional solvers, we only need to see examples of their dictionaries that are passed to OpenFOAM, and we can create a new GUI for them. So,
same for the Tecplot part. We can basically load, develop data loaders depending on your specific tools, and that's something we can do. So basically the whole package of cfMesh, CfSuite, and Tecplot 360 allows you, whatever software you are using, basically to integrate that fully into a GUI from within every step within your workflow, actually. All right. Getting support from creative field. Yep.
So as for support, our cfMesh can always is a project on open source. You are free to download it, build it yourself. You are completely free to use it. I see right now that I have received a question if using CfSuite the user no longer has access to use open source code. You do have access to use cfMesh, which is open source. It is provided in the installer of our application, but it is not licensed, it is for free. As for CfSuite, it is commercial, it is not open source, but it comes with OpenFOAM and cfMesh that you are free to use. So for cfMesh, as I said, for cfMesh you can go to this address at SourceForge and you can contact us. For CfSuite, you can download it from our website with a 2 weeks license, and you can always contact us at this email for licensing information and for any support that you may require.
All right. From Tecplot, if you wish to get information, so first of all, you can trade for free at tecplot.com/trial. If you have any question, please email us at support@tecplot.de, and if it's an urgent question, just call us. We will answer you within minutes, and that's from experience the best way for us to provide you support. We can organize easily online meetings or webinar trainings, and another site of interest is tecplottalk.com, which is the user forum, on which you will find useful add-ons, some data loaders, some tools such as macros, Python scripts, and so on. All right. Thank you very much. We will remain online for a few minutes to answer any question you may have. Thank you again, and don't hesitate to contact us. For Genias Graphics, myself, Antoine.Lager@genias-graphics.de, and for CfSuite or cfMesh, Tomislav Lugarich. So tomislav.lugarich@cscorefields.com. Thank you.